Hello everyone, welcome back to the EC Fundamentals 1 lecture series. In this lecture we're going to talk about resistors connected in parallel. You probably have already watched the video about resistors connected in series, which was related to Kirchhoff's voltage law. And here we're going to use Kirchhoff's current law, or KCL, to find out what is happening when we're connecting resistors in parallel. So specifically the arrangement we're going to focus on is shown in this particular figure. You can see that we have several of them, n in this particular case, and we have been able to take all of the upper nodes of these resistors and put them together, and we've been able to take all the lower nodes of these resistors and put them together. By doing that, we have achieved one very crucial thing, and the very crucial thing is that the voltage drop across all resistors is exactly the same. So across R1 is V, across R2 is of course V, across Rn is of course V. So in fact this is exactly the indication that we have resistances connected in parallel. The voltage drop is identical for all of them. And that should be the way that you check if resistances are connected in parallel or not. You should be asking yourself, is the voltage the same? If it is the same, then they are in parallel. Don't necessarily rely on just the image that you see here. The image that you see here is made for training purposes, and we have basically made the resistors very nicely drawn so they appear literally parallel to each other. In real life, there are many other configurations that you might see. Well, they don't appear as clean, but still the voltage drop is exactly the same, and therefore the resistances are indeed connected in parallel. Now, when we have something like this, we can go ahead and replace the resistances with the Req, the equivalent resistance, which we discussed in the previous video. And the goal here is to find out exactly what this Req is. As you might recall, we defined Req, the equivalent resistance, as the ratio of V by I. Or to say it differently, we're asking the question, what should that resistance be such that the current we draw from the two sources is exactly the same no matter what. So, in order to find this Req, all we have to do is apply KCL at the upper node, which is the node where all resistances are connected to. So, if I apply KCL, I will write down that all the currents leaving this node must add up to 0. And when you do that, you will get that negative I. This is the current that is entering the node, and therefore I will take it as negative, plus I1, plus I2, plus all the currents until In must be adding up to 0. Or I can write this as I, if I take this current to the left-hand side, will be equal to I1. Well, but I1 can be written by Ohm's law as nothing else but V divided by R1, plus I2, which is V divided by R2, and so on all the way to In, which will be V divided by Rn. Now, if I divide both sides of the equation with V, I will get that I divided by V is equal to 1 by R1, 1 by R2, plus all the way to 1 by Rn. So by looking at this equation, essentially we have been able to find out the equivalent resistance. Why? Because this left-hand side here, the I divided by V, is simply equal to 1 divided by Req. So this is a very famous equation. Specifically, I will write it in a slightly different way, that 1 by Req is equal to the sum of 1 over Ri. And this is the most famous equation, the most interesting way of writing down what is the equivalent resistance for a parallel combination of resistances. It's an equation you should memorize. It's an equation you should be able to apply immediately. You don't have to prove it. It's something that is really well known and quite useful in real life. Now, there's a different way of writing this, simply by remembering that the inverse of resistance is called a conductance. So in other words, since 1 over Req is equals to G equivalent, the equivalent conductance, I can rewrite exactly the equation I gave you before as basically G equivalent is the summation of all conductances. And this is another very famous way of writing the fact that I can add up conductances connected in parallel as opposed to adding up resistances, which was the case when we were talking about connecting resistances in series. So to finish that proof, I want to remind you that we applied KCL at the essential node where all resistances are connected to, and we found out that you can replace the parallel combination of resistances by one resistance, and the value of this resistance can be found either by summing up all the conductances to find out the equivalent conductance, or by summing up the inverse of all the resistances to find the inverse of Req. Both of those are equivalent, and you can essentially apply them anytime you want. Now, there are some interesting cases here that I would like to highlight that follow up from this proof. The first thing I would like to highlight is what you see here as number 1. So the equivalent resistance is actually smaller than the smallest possible resistor when you connect them in parallel. So when you have basically the parallel connection, the resulting equivalent resistance will always be less than each of the individual resistances connected in parallel. So let me give you a quick example here. So let's suppose that I connect 3 resistances. One of them is 6 ohms, the other one is 3 ohms, and the last one is 2 ohms. Now, if you go ahead and find the equivalent resistance of this combination, you will find out that this equivalent resistance is just 1 ohm. And essentially, this is a quick example that verifies what I said before. The equivalent resistance of 1 ohm is smaller than the smallest resistance that you get. So that's something to keep in mind. Another way to phrase that from a more practical perspective is that you can never raise the resistance when you connect things in parallel. You can only make things smaller. This also brings another interesting point of what happens when you connect identical resistors in parallel. When you connect identical resistors in parallel, essentially you will get the value of resistance divided by the number of resistors that you connect. So let me make this more clear. So let's suppose that I have an R resistance here, another R resistance here, another R resistance there, all the way until I basically get n of them connected in parallel. So when you do connect n of these resistances in parallel, you will basically get an Req whose value will be nothing else but the amount of resistance you have, which is R, divided by the number of resistance you have, which is n. So this equation, of course, is directly derived from the equation we just learned before, but because it's such a common case, it's probably worth remembering that. Also, for the case of 2 resistors, so you can clearly see that your Req will simply be half of the resistance that you connect. So Req will be R divided by 2. Now, for the case of 2 resistors in parallel, there is also another expression that is very likely that you will see in real life. So let me try to derive that. So let's say that I have 2 resistors, not identical right now, just 2 general resistors, R1 and R2, and I'm asking the question, what is the Req? Of course, I can go ahead and apply the equation I have before. So if I do that, I will get that 1 divided by R1 plus 1 divided by R2 will be equal to 1 divided by Req. And if you do the algebra a little bit here, you will find out that Req will be equal to R1 times R2 over R1 plus R2. Now, this situation occurs so often in real life that honestly it's worth memorizing the expression that you see right here. And the expression that you see right here gives you very quickly, explicitly, the equivalent resistance for the case of just 2 resistors connected in parallel. Essentially, you can write this as the product of the resistances divided by the sum of the resistances. And it's an equation worth remembering, again, because the case of 2 resistances connected in parallel happens in real life quite often. Now, in addition to finding the REQ, there is another really important equation that you should keep in mind, and that's related to the concept of current division. You might recall that when we talked about resistors connected in series, we had voltage division. And in a voltage division, the whole idea was that voltage is distributed proportionally to the value of resistances. So when you had resistances connected in series, more voltage drop would exist across a large resistance versus across a small resistance. Basically, the same thing happens here. When you have an amount of current that basically flow through these resistances, the amount of current that each one of these resistors will get will be proportional now not to the resistance, but rather to the conductance. We found out before that the amount of current that you will have will be equal to the voltage drop divided by the conductance, by the resistance. So for example, I1 here will be equal to V divided by R1. But if you look at this current here, which of course should be the same since we have REQ, you can also write that this I here will be equal to V divided by REQ. Or I can write down that V here will be equal to I times REQ. So I can essentially go ahead to my previous expression here on the left and write down that I1 will be equal to I times REQ divided by R1. Now let me slide this in an equation that essentially shows more explicitly the current division that is taking place. I can write down that I1, the current flow through the first resistance, will be equal to the total amount of current, I, that I will get, times G1, I'm bringing 1 over R1 to the numerator, over GQ. So I wrote essentially that REQ is equal to 1 by GQ. And one more step, this will be equal to I, G1, and remember that for the parallel case, the equivalent conductance is nothing else but the summation of the conductances. And that expression here for the current that I derive for the first resistance, I1, is a very common expression, most often is referred to as current division, which basically tells you that the total amount of current that you're drawing from the source, right here, will get distributed to the different resistances in the circuit proportionally to their conductances. So this second equation that we're deriving here, called current division, is as important as the first equation we derived for the equivalent conductance or the equivalent resistance. They literally go hand in hand, and you should make an effort to remember and apply both of them equally well. So there are, in other words, two branches of learning for the parallel combination of resistances. One branch is related to finding the REQ itself, and you already have an equation for that. And the other branch is being able to immediately, by applying the current division formula, to find out the amount of current that each one of these resistances is getting. So just make sure that before you apply either of those two expressions, that you're confident that the resistances are indeed connected in parallel, and the way you do that is by ensuring that the voltage drop across each one of them is the same. So this was the last comment I would like to make for today's lecture. Thank you for watching this. We will see you next time.